All right, I'll begin with a word of prayer. So, Heavenly Father, we just thank you again for this opportunity we have just to meet together and study math. We thank you, Lord, for your many blessings to us this day. I just ask you bless this class and just add to our understanding, Lord. In your name I pray. Amen. All right, so last class we introduced, what's a normed vector space, right? And at the very end of class, I got basically to the definition of what's a limit. So let me just start with that again. So our goal today basically is to study continuity over a normed linear space. All right. So if everything goes as I hope, by the end of this class, we will pretty much understand how to analyze questions of limits and continuity over normed vector spaces. So. All right. So first of all, definition. We say that if you have a function from v to w where v and w are normed linear spaces with norms v, and so I just put a little sub v and a little sub w. Oh, I don't need all that. Good grief. What's wrong with me? I already defined that last time. Apparently I prepared too long for class today. There's some kind of careful balance that you have to strike. Too much preparation leads to bad lecturing. So, for some reason I woke up at 6:30 today and I've been thinking about it since then. Anyway, limit as x goes to x naught of f of x is equal to f of x naught. If this and this holds, then what do we say? F is continuous at x naught, right? So we define continuity at a point in the usual way, in terms of the limit we defined last time, right? That limit is a notational convenience that hides an epsilon delta argument, right? Okay. So we can also define limits in terms of sequences, although I don't think I actually do that today. But let's talk about sequential convergence. What does sequential convergence look like? Definition. If we have a sequence, a sub n, all right, in, say, V, a normed linear space, then what? Then we say that the limit as n goes to infinity of a sub n is equal to L. All right, so a sequence, again, is what it usually is. It's a function from the integers. And for notational convenience, you could say the positive integers with 0 tacked on. That's often what we do. Or you can do n equals 1 to infinity. Anyway, it's got to have a start. It doesn't have to have an end. It's a function from some subset of the integers with the successor property into your space. That's a sequence. So you can think of it as it being essentially an ordered list, right? So when do we say that ordered list has a limit? Well, this is our notation for it. Limit as n goes to infinity of a sub n equals to L. Now that is what that means. What that's interchangeable with is the following. If for each epsilon greater than 0, there exists big M in the positive integers n such that the norm of a sub n minus L is less than epsilon for all n greater than m. And so I don't know if you recognize it or not, but that's the usual definition of sequential convergence. And I say usual in the sense of by comparison to real analysis, by comparison to calculus 2 perhaps. Maybe not. Maybe we didn't give you, well, I think we do go this definition in calc 2 here. All I've done really though is replace the absolute value with the norm, right? And to be more specific, of course, I'm talking about the norm in V, right? Now, one of the things we learn in real analysis is that the study of convergence is greatly assisted by the introduction of something called the Koshi Criterion, or more specifically, what's known as a Koshi sequence. So let me give you the definition for that. AN is a Koshi sequence if and only if for each epsilon greater than 0 there exists m in the positive integers such that if you have m and n greater than big M, I'll put feet on my big M. Feet. So if m and n are greater than big N, then that implies that the norm of a sub m minus a sub n, m as in mummy, n as in nanu, less than epsilon. All right. So, you know, the difference between the definition of convergence and the difference of Cauchy is it doesn't look too different on first glance, but the difference is the Koshi criterion just depends on elements of the sequence, right? Whereas the definition of just straight convergence involves the sequence and the limiting value, right? It is in fact true that if it's convergent, it implies it's Cauchy, all right? But the converse is not generally true. You can have a Cauchy sequence which is not convergent. For example, convergent implies Cauchy, but Cauchy does not imply convergent. For example, let's see here. Let's see here. What's a good example of that? I'll keep it real. How about this? A sub n is equal to. I'm trying to think something here. I don't know. How about the sum? Let's see here. How about the sum n? Let's say I gotta use a different letter. Sum k equals 1 to n of minus 1 to the k over k. This is the alternating harmonic series. I think I'm missing a sign here. There, that's better. Now, so if you look at this, what happens? You got A1 is what? 1, right? A2 is 1 minus a half, right? A3, 1 minus a half plus a third and so forth, right? In fact, if you draw a number line, you can kind of see it's zeroing in on some value, right? Now, every element in this, well, this of course is a series, very, you know, but every element in the sequence, right? These are the sequence of partial sums for this series, but every element here is a rational number, right? 1, a half, whatever that works out to. I can't do math. What is it, 5/6, so forth. Now, does this sequence converge? In fact, it does. In calculus 2, I will show you that the limit as n goes to infinity of a sub n, in fact, is the natural log of 2. Right? Now, the natural log of 2 is not a rational number. This can be proved. Right? So, this is the sort of context in which this implication fails. If I look at a rational sequence, all right, a sequence in the rational numbers, it doesn't have to be true that a Cauchy sequence of rational numbers converges to another rational number. There are holes in the rational numbers. There's things missing. In particular, the so-called irrational numbers, natural log of 2 being one of them. So, when this implication is met, for arbitrary Koshi sequences, that means we're working with a very special kind of space. Such a space is called complete. So, if Koshi implies convergent for all sequences, then we say the space is complete. Now, we're mostly interested in norm spaces, but the definitions I'm talking about right now work for metric spaces, as I talked about last class. I mean, so you actually, this discussion works outside the context of linearity and all this. But we're mostly interested in normed linear spaces. A normed linear space, which is also complete, has a special name. It's called a Banach space. A complete normed linear space is a Banach space. Banach spaces have the most beautiful theory of analysis, or you could say the most simple. There's much that's known even in the infinite dimensional context for Banach spaces. It's a very nice place to work. At the same time, it's limited. Not all applications are covered by Banach spaces. So if you want to be an analyst, you got to think a little bit bigger than this, but it's a good place to start. Now, so the proof that the real numbers are complete is not a problem for this course. That is a problem for Math 431, for an honest-to-goodness real analysis course. It is technical. It is dirty. It is subtle, okay? But what we can do in here is we can use the completeness of the reals to prove the completeness, for example, of R2. And I'd like to show you that argument. And then I'm going to show you how we can use this completeness notion to prove something a little bit more interesting. In fact, that the matrix exponential converges, right? This is the right toolkit to answer such a question. So why is R2 complete? Proposition: if R is complete, then R2 is complete. That's my claim. So here's the proof. So let's take, we have a sequence, let's say x sub n, y sub n. Suppose that this is a Koshi sequence in R2, right? What's that mean? That means that for each epsilon greater than 0, there exists some m in the natural numbers such that m and n greater than n implies what? The norm of xm ym minus xn yn is less than epsilon. That's just the definition. That's the Koshi criterion. Although I think the Koshi criterion may be something a little bit different when you take real analysis, so I should probably stop saying that. This is the thing that makes a Koshi sequence a Koshi sequence. Okay. All right. Then what is this? Well, notice that the norm of x, so that's the norm of x. Let me call this thing, so I don't write it again, let me call this thing star. Okay, notice that star is equal to the square root of what? It's the square root of the absolute value of xm minus xn squared plus the absolute value of ym minus yn quantity squared, right? So we have the sum of the square root of the sum of two squares, right? So I think we can all agree that that should be less than or equal to the absolute value of xm minus xn, or the absolute value of ym minus yn, right? Actually, you shouldn't agree with that. you should say that's crazy. It's exactly the opposite, right? If I add, this should be larger than either one of these things. So, other way around, right? So what does that give us? So, we have that the absolute value of xm minus xn and the absolute value of ym minus yn is less than or equal to the square root of this, well, let me just get to the point. It's less than or equal to star, right? But that's less than epsilon, right? So you see, we can use the same big M to argue that the sequences in R, right? So thus, I'll put it in a different color. Thus, xn and yn sequences in the reals. All right? So what does that mean? The reals are complete, right? Thus, there exist, let's say, x and y in the reals such that xn goes to x and yn goes to y as n goes to infinity. So I claim that xn, yn goes to xy as n goes to infinity. I have a potential point, which is the limit of the Koshi sequence in the plane. Now we just need to prove it actually is the limit. So what you do, I mean, I have a proof in the notes which shows this from base principles here. So let me just do that, I guess. I'm kind of torn. We could just apply a theorem I'm going to prove later today, but so let epsilon be greater than 0. Choose, let's say, n sub x and n sub y. Maybe I should say m. Come on. M sub x and m sub y greater than 0, such that what? Absolute value of xn minus x is less than epsilon over 2, and the absolute value of yn minus y is less than epsilon over 2. I'm going to start over up here. We'll choose n, big M, equal to the maximum of nx and ny. Right? If I do that, if n is greater than m, then the norm of xn, yn minus xy is equal to what? It's equal to the well, it's less than or equal to, of course, the norm of xn minus, excuse me. That's equal to, of course, the norm of xn minus x, yn minus y, which is equal to the square root of what? Absolute value of xn minus x quantity squared plus yn minus y quantity squared. And then by the triangle inequality, that's less than or equal to the absolute value of, sorry, I mean, there's various ways you can come to this, but you should get this. I mean, but then because the xn and the yn sequences were Cauchy, we're able to control that they converge, and so I can control how far xn is from x for a sufficiently large n. In particular, I choose to control them to be within epsilon over 2 units. So this is less than or equal to epsilon over 2 plus epsilon over 2, which gives me epsilon, which then shows, of course, that the Koshi sequence in the plane converges. Now, one of your homework problems is to show that Rm by n is complete. The argument is the same. Essentially, what you want to do is you want to look at a Koshi sequence of matrices and then through an inequality argument similar to this, argue that each component sequence is Cauchy. But then by the completeness of the reals, it converges, and then you can take the matrix of those limit points as the limit for the Koshi sequence of matrices. Pretty much you can rip off this argument. It's really easy to see how to do this for Rn, right? If you can do it for R2, you can do it for R3, you can do it for R4, and so forth. Now, anyway, so that's, once you have that one basic thing that you know that the real numbers are complete, that's huge. Oh yeah. Okay. So let me sketch for you an interesting application of this. I think we don't need this anymore. So do you guys know what the matrix exponential is? This is a fun example for us to work on. So here's the definition of the matrix exponential. E to the a is equal to the identity matrix plus a plus 1/2 a squared plus da, 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 da. Now, more formally, I could say it's the sum, let's say k equals 0 to infinity, of a to the k over k factorial. So basically, it's the power series, or the Maclaurin series. Haha. It's the Maclaurin series for the exponential function, just with power of a real variable replaced with a matrix power. A has to be square. Now, you'd be like, okay, well, which matrices does this series converge for, right? I mean, does this work for all matrices, or is this matrix exponential something you can only calculate for matrices which are of a particularly special type, right? So we can investigate that question using this notion of Cauchy and complete and everything. In your homework, you're going to prove that our m by n is complete. So, of course, square matrices give you a complete space, right? So I'm going to argue that this, in fact, converges for any matrix. Let me show you how. So consider, so we're going to have to talk about the nth partial sum, right? So the nth partial sum of a series of matrices, it's the same, right? It's like take sum k equals 0 to n of a to the k over k factorial. There's your nth partial sum, right? And so this, to say that this really exists is to say that we're really looking at the limit. I mean, this is just a symbol to a shorthand for the limit as n goes to infinity of the nth partial sum, right? The series exists if and only if this sequence converges, actually. Now, I'm going to argue that if you know a few things about matrices, let me show you. So let's just get to it. Let n be greater than m, and consider Sn minus Sm. What would that look like? So I don't want to write it out. Just think about it in your head. What would happen with these sums? You've got the sum from 0 to n, and you've got the sum from 0 to m. You're subtracting from 0 to m. What happens? You cancel from 0 to m, right? So this should simplify just to the sum k equals m plus 1 to n of a to the k over k factorial, right? So that's just a algebra, finite things canceling. Let me call this star. So then, if we look at the norm, the Frobenius norm, all right, so that one we define by the sum of the entries of the matrices strung out, right? The Frobenius norm will be equal to, well, by the triangle inequality, it's equal to this, less than or equal to the sum k equals m plus 1 to n of the norm of a to the k over, well, I can pull the k factorial out, right? It's a number, so it pulls out of the norm, k factorial. And so I have the norm of a to the k, like that, by triangle inequality for the Frobenius norm. And then here's a really interesting fact about the matrix norm. In fact, the set of square matrices with the Frobenius norm forms what's known as, it's called the Banach algebra. It's more than just a complete normed linear space. It also has a multiplication, and the way it works is if you look at the Frobenius norm of the matrix A times B, it's actually less than or equal to the norm of A times the norm of B. So this is kind of like Cauchy-Schwarz, but for matrices. That's not an easy thing to prove. That's one of your homework problems if you want to attack it. That to me is a very challenging homework problem. I'm going to try to give you guys some guidance. There's kind of a strategy to prove it. It's kind of an awful thing to prove, though, okay? But it's true. So with that in mind, if you use induction, right, it then follows that the norm of the kth power is equal to what? Well, actually, this is equality. This is actually, well, goodness, is that equality? You know, I'm not absolutely sure. I'll tell you what, I'm going to put a less than or equal to because that's all we need. I'm not sure if this result can be strengthened. I kind of think, well, I just don't know. Forget. Anyway, that's definitely true. Maybe you can make that equality. So with that, I can trade this for this, right? Now, at this point, I'm going to steal something from calculus 2. The exponential is well defined. So the Taylor series for the exponential converges. But it's an exponential of a real value. Right? So in particular, if I take n and so like this, I argue is of course less than or equal to e to the norm of a. That's probably a strict inequality. E to the norm of a would be this, just letting it go to infinity, right? Letting n go to infinity and throwing in the start of it from 0 to m, and then, so throwing in this, basically the start finite tail and the end infinite tail, and then that would be the exponential. Oh. But I'm an idiot. That's not what that just shows it's bounded. Actually, I did this earlier today. I thought I got this out of my system. That's true, but useless to us. Sorry. Let's think about this. So let little s sub n equal to the sum k equals 0 to n of the norm of a to the k over k factorial, like that. So this is the nth partial sum of the ordinary exponential function. All right. You guys with me? So if you look at this, I can rewrite this, right? I can basically undo the cancellation step I did up here, and I can say, aha, that's really equal to s n minus sm. And I can put the absolute values here because of the way I did things. Right? But then that essentially completes the proof because this is a convergent sequence because the exponential of any number exists. So since the little sm is a Koshi sequence, that means that I can control this difference. I can make it as small as I like for m and n sufficiently large, and consequently I pin down this, which shows that the big S and the big S sub n is also a Koshi sequence. Hence, by the completeness of the set of square matrices, the matrix exponential converges for any choice of A. That's how we use completeness to actually do things that are interesting. Yeah. I think the question of whether or not this exists for all A is an important question to everybody, because matrix exponentials you can calculate all kinds of things with. Solutions to differential equations, for example. You want to solve the differential equation x prime equals to ax. The solution is e to the at. That actually gives you a vector. Every column in that matrix is a solution to that differential equation. And linear differential equations are at the heart of all applications to engineering and physics. And we'll throw chemistry in too. Biology, fine. Fine. Biology. Are you happy? All right. Biologist. All right. So I wanted to, I mean, it's nice to define Cauchy and talk about completeness of the plane, but I think it's interesting to actually look at an example that's got a little bit more depth to it. And you'll forgive me if I haven't written all the details out there. Okay, so as I had advertised, we're looking to understand the properties of continuity and limits in normed linear spaces. So our next agenda item is proposition 2.3.7. All right, so we have V and W normed linear spaces, and an element of V, a limit point. What's a limit point? Well, so notice I'm taking the domain of F to possibly not be V, and I'm also taking the domain of G to possibly not be all of V. All right? So to say that A is a limit point just means that I can take a limit at that point, right? You've got open neighborhoods around the point to actually take the limit. See, because you could have weird domains that have points which aren't limit points, right? And then you'd need to have a separate discussion for those sorts of points, those so-called isolated points. Anyway, that said, really simple. 1, the limit as x goes to a of f of x plus g of x is equal to the limit of f of x as x goes to a plus the limit as x goes to a of g of x. And 2, the limit as x goes to a of a constant times f of x is equal to the constant times the limit of f of x for, of course, c in the reals, provided what? There is one important thing we need to have provided in order to say 1 and 2. Limit of a sum is the sum of the limits when. Here, let me show you a violation. What's that? No. How about this? Limit of 0 is 0, right? So, okay, the limit as x goes to 0. So the limit of 0 as x goes to 0 is equal to the limit as x goes to 0 of 1 over x minus 1 over x, right? So that's the limit as x goes to 0 of 1 over x minus the limit as x goes to 0 of 1 over x. No, this is not allowed. Why? Yes, these limits do not exist. In order to apply the limit laws, we must apply them in such a way that, you know, whatever is the children of the parent limit, they're actually, they exist, right? They're not, the kids aren't too bad. So we do need to suppose that these limits exist if I'm going to be able to add them like that. No, to say it's a limit point means I can ask the question whether or not the limit exists. I know, right? Yeah. Right. The limit point doesn't even have to be in the domain of the function. Like certainly 0 is not in the domain of 1 over x as a function. And yet I can calculate the limit at 0 and determine it doesn't exist. That is the subtlety and also the usefulness of limits. It gets us right past the point where algebra makes sense. So provided limit f and limit g exist where? They're not real numbers in this case. They're in W, the normed linear space. Now, I don't know if you had Calc 1 with me, or I mean, I think most of us proved this in Calc 1 here. So here's the proof of 1. Let let epsilon be greater than 0. Choose delta f and delta g greater than 0 such that what? 0 less than absolute value, not absolute value, norm of x minus a less than delta f implies what? How about f of x minus, it helps to come up with, it's kind of a drag to write limit, blah, 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 blah. So we can just call this thing something, all right? Let's call this L sub f. Let's call this thing L sub g. We're assuming that those exist in their elements in W, right? So we want to assume that f of x minus L sub f, the norm of that is less than what? Epsilon won't work. Close though. Right, because we're also going to do delta g so yeah, choose epsilon over 2 and epsilon over 2. I mean, this is not obvious. This is something you would work out some scratch work, and then we come back to this argument. I'm not showing you the derivation of the proof. I'm just showing you the proof, right? And just to comment again on the difference between here and Calc 1, these are the domain. We're talking about the norm in V. The range, we're talking about the norm in W. But otherwise, the song remains the same. I mean, so then consider, then if you look at the norm of f of x plus g of x minus L sub f minus L sub g, right? We'd like to show that that's less than epsilon. Although I'm skipping a step here. My mind skipped a step. What am I need to choose a delta, right? So here's the delta we choose. Choose delta equal to the minimum. See, we use the maximum for the Cauchy argument we just did. It's kind of dual, right? Because you look at the tail of the sequence to prove things. But with these epsilon delta proofs, we kind of squeeze in on the point and we let things go to 0. So there's that duality between infinity and 0 that people like to talk about. Anyway, delta f, delta g, choose a minimum there. That and let x be an element of V such that what? 0 less than absolute value of x, absolute value norm of x minus a, in the V norm, of course, less than delta. With respect to that, such x as that, then I can do the triangle inequality here, right? I can do the triangle inequality, break it up into 2 pieces. Now, if you didn't have if you didn't have calculus 1 here, and this is totally unfamiliar to you, that's cool. I mean, don't panic. Everything's okay. So this is what? That's the triangle inequality for the norm. But then by our construction, that's why we chose epsilon over 2 and epsilon over 2, right? Aha! So therefore, the limit as x goes to a of f of x plus g of x is equal to L sub f plus L sub g, but that's exactly the claim written in a slightly non-standard notation. The first time Dr. Wang taught calculus 1 here, he put the proof on test 1 for the limit. Remember those students were like, "What was that?" Ah, it was funny. I think he's mellowed a little bit since then, but I don't know. How would you prove 2? To prove 2, basically you just use epsilon over the absolute value of c. Right? So we have the sum of the limit. Joe! Sweet! I have until 1:15. Yes! This is only a believable excuse right now, and I appreciate it. It's very I mean, I'm well played.
I have a class at noon on Monday to Friday.
It's okay. What we're doing right now, Joe, is we've been proving that basically we've been exploring the fact that arguments from calculus 1 just as well work in the context of normed linear spaces with the correct adjustments. Basically, the adjustment we're making is to replace the absolute value with the norm. But that's a lot of it. I mean, that's most of it. Now, what else? What other powerful theorems did we have about limits in calculus 1? I mean, linearity, the limit's huge, right? Once you have this, you can prove that the limit's unique. This proves that you can prove that the limit's unique. Why is that? Remember, if we have a limit of f minus f, well, that should be the limit of 0. So if the limit of f exists, limit of f minus limit of f is equal to 0. But if these were two different things, that would be a contradiction. So linearity immediately gives you uniqueness of the limit, which is nice, because that means if you use the limit, you can define functions with a limit in a single-valued way, right? Limit being unique means if I define some formula for some new thing using a limit, then it's single-valued if it's unique. You might ask the question, so are you saying there are limits which are not unique? Is this just a vain exercise and blah, blah, blah? No, it's not. In topological spaces, there are more general spaces where limits are not unique. If you have spaces which are not Hausdorff, you have these awful things, non-unique limits, whatever Hausdorff means. Anyway, when you study topology, you'll learn it there. What other theorem do we have in calculus 1, though? How about the sort of the chain rule for limits? If we have remember the other one? If we have the limit of f of g of x, sometimes we can say that's f of the limit of g of x, right? That was another theorem we had. Putting on the appropriate, assumptions. If f is continuous, we can pass limits inside it. That's something we used sometimes. What was the other major theorem we had for limits in calculus 1? What's that? Yeah, I guess L'Hopital's is kind of technical, so we stay away from it. Of course, L'Hopital's is super useful, yeah. Squeeze theorem is the one. Squeeze theorem is really subtle in the sense that Squeeze theorem allows you to prove the existence of a limit by just putting it between two other limits which exist. So it's a little bit, more. And so I actually have, I don't want to, let me just, project it. So I will not I will not subject you to me writing out the proofs of either the composition, the composite limit rule, or the squeeze theorem, but I want to show you. Let me just do some show and tell here for a minute. That their proofs, well, I mean they're not even that tedious really. They're just kind of the usual proofs. Well, maybe they're the usual proofs that you didn't see also, right? And I'm not sure what the right time in your education is for you to see them. For some of you, it's never. I'm talking to the engineers, right? You need to be able to use them and maybe internalize its concept. But the proof probably doesn't matter to you. But there are math majors here, so you can humor them, right? So here's the proof of the composite rule. Basically, what it involves is just systematically choosing a delta that makes the next epsilon small enough, that makes the next epsilon small enough, and you just kind of make a chain of them, and then they just work together to give you the needed consequence. But it's not too hard to prove that. You can read that. I understood it this morning. I think it makes sense. So that's in my notes. And then the squeeze theorem. Squeeze theorem is a little bit harder, but what I did to prove the squeeze theorem here is basically I just looked back in my Calc 1 notes where I proved it, and I just replaced absolute values with norms, and it made sense. So the usual proof for the squeeze theorem in Calculus 1 adapts nicely to here. Of course, I'm talking about real values. It's not just for, that wouldn't make sense for functions from V to a vector space, We're talking about real valued functions with a domain being the vector space. All right. So, but for real valued functions, we can do that. All right. So, at this point, I told myself to put away the projector. Take my own advice.
I'm gonna hand it to you. Your notes look a lot more like a textbook.
They look more like a textbook than they used to. Oh, well, that is. Ah, yes, the neatness that is just it's inevitable if I use LaTeX. It makes me look neater than I actually am. That's the joy of LaTeX. Although the curse is that I don't have a spell checker, or an editor, or much common sense. So they're still my notes. What's that? Ah, thank you. No spelling. Let us revel in our ignorance. I mean, but in defense of those who are ignorant with spelling, right? If you're ignorant of spelling, if you just open up any computer and you start typing, like, it fixes it for you, right? But, right, but if if you're like typing down a tensor calculation, there's not going to be like a red underline, right? Ah, yes, okay, you have a good point. Word will not understand it. It will put a red underline. But my point is, well, anyway, I think. Oh, wait a minute. Now I remember you. This was like every day in Calculus 3. Okay. Wasn't it Calculus 3? Physics 2? Oh, Physics 2, yes. You guys know I'm distractible. Why are you doing this? We have things to cover today. You would like me to rip off this Band-Aid so it's off. So past today, we don't have to keep talking about continuity, because I know you guys aren't that interested in continuity, but at the same time, I want to give you a complete description of it, right? So, okay, so here's one we can prove. If we have a function f from a normed linear space to the reals, defined by what? How about this? F of x is equal to the norm of x, all right? We can show that this is continuous everywhere. This is going to be a little bit easier than the thing we did with the exponential earlier. Okay, so now this time, Daniel, your go-to choice for delta will work. Let epsilon be greater than 0. Choose what? Delta equal to what? Epsilon. Yes. That will work here. But of course, we have no evidence that will work just yet. Here's the fundamental idea. Notice. Excuse me. Notice that the norm of x. Oh, sorry. Let a be what? Let a be some point in V. I don't care which one. All right. And also let x be, well, anyway, x is also in V. All right. So the norm of x is equal to what? You can add 0, right? X minus a.
Number of
Plus a. So, of course, this is less than or equal to the norm of x minus a plus the norm of a by the what? By the triangle inequality for the norm, right? All right, so suppose, let's see here, the 0 less than the norm of x minus a is less than delta, and consider, so what do we want to do? We want to consider, oh, what am I doing? What was the claim of the proposition? This is kind of like Trump's policy statement. But, I mean, I love Trump, don't get me wrong. I think he's hilarious. I was thinking about it today earlier. A vote for Trump is a vote for none of the above, and that is why he will win. It's a vote against the Republicans, and it's a vote against the Democrats. It's a vote against Washington, D.C. How can he not win? Think about it. You're like, you could have a gaffe. No, I don't think so. Well, I don't know. We'll see. I don't see any, I don't know. Okay, so that was my fault. That wasn't Joe's fault. Okay, so then the claim is the limit as x goes to a of f of x is just equal to f of a. In other words, you know, the limit as x goes to a of the norm of x is just equal to the norm of a. All right? The norm is continuous. Another way of saying it. Okay? Okay, so to prove that that limit exists, we have to show that the norm of f of x minus f of a, which is, by the way, what? That's the norm of x minus the norm of a. Now, I should be a little bit lazier here. What's the norm for the real numbers by default? Absolute value, right? So I shouldn't really write double bar here. I can just write single bar. It's the absolute value, okay? But what did we just show in the little preamble here? This little argument right here shows that I can replace the absolute value of x with the absolute value of x minus a plus the absolute value of a, right? Excuse me, I'm saying absolute value. I should be saying norm. This is less than or equal to the absolute value of the norm of x minus a plus the norm of a minus the norm of a. The norms, they be canceling. Chunk, chunk. And of course, the norm of x minus a is positive, so you can drop the absolute value. Anyway, this is less than delta, which is, by the way, equal to epsilon. Game over, we win. So that shows that if you're within delta units of a, you're within epsilon units of the limiting value for the output of the function. So the limit exists. All right? It's copacetic. When does this class end? 12:30. All right. Give us a chance to breathe here, and I'll start my next battle. My temptation is to not show you the details for the next proof, but I really should show you the details. This is an important one, and it really lies at the heart of much of what we do in the rest of the course. I mean, we're using this, whether we realize it or not, in many, many places. And I don't think this is that easy of a proof, but it's not insurmountable either. So here it is. Theorem. And this is a really nice theorem. It states the following: if you've got a function f from one normed linear space to another, and a is an element of v, right? Then, oh, a little bit more notation, sorry. And if you also have that beta, which is, by the way, w1 to wm, a basis for w, all right? Given that, the limit as x goes to a of f of x is equal to big B, which, by the way, is the sum j equals 1 to m of b sub j, w sub j. So I'm just expanding it in the beta basis. Those are uniquely given from the linear algebra. There's nothing to prove there. I'm just laying out the notation of what big B is. This is interchangeable with this. The limit as x goes to a of f sub j of x is equal to b sub j for all j equals to 1 to m, where f is equal to a sum j equals 1 to m of fj. I mean, let me put it into words. If you have a vector-valued function, its limit exists if and only if every component function of the vector valued function has a limit which exists. So if we have a function which maps into R4, you can just look at the limit of the function in the first slot and the second slot and the third slot. But you can break it up into just always looking at real valued functions essentially, and look at the continuity or the limit of each one of those component functions. So this is a very nice theorem, because it means essentially that we can always be looking at real valued functions in some sense, which is a great simplification, right? All right. So here's the proof. In my notes, I have this written about 30 times in the proof. I think for the sake of not writing that 30 times, we're going to come up with a name for this that's easy. How about L sub j? So that is simply the length of the jth basis vector. It's a basis vector, right? So it's non-zero. So this is not equal to 0, which means we can divide by it, okay? We're going to use that throughout my argument. So the forward implication. Suppose the limit as x goes to a of f of x is equal to b. All right? And we'll let f sub j be as in the theorem. Notice the following. If you look at the absolute value, excuse me, good grief, the norm of f sub j of x minus b sub j times wj, so that would be like the jth vector projection. If you want to think about it that way, it'd be like the jth component as a vector of the difference f of x minus b. That is less than or equal to things, right? I can just add all of the other pieces, right? It's less than or equal to f1 of x minus b1 w1 plus da-da-da-da plus fm of x minus bm wm. Huh. I'm not sure I entirely believe that right now. I think I may be assuming orthonormality of the basis right here. Let us foolishly forge ahead, as there's no hope I can fix this if it's an error at the moment. Was that the sound of my proof dying? I have this vague recollection of Spencer going, ah, and then I'm going, but obviously I didn't remember the, and I talked myself into it again this morning. I'm not sure that that's true, but if it was. Again, it's definitely true if you have some inner product and these are orthogonal with respect to that inner product. It's for sure true. But anyway, this is exactly the expansion of f of x minus b written out in the basis. It may still be right, and I'm just talking myself out of it. We'll talk about it after class. All right, therefore, I mean, the theorem is true whether or not my proof is on the level. Therefore, if you look at the f sub j of x minus b sub j, well, that's equal to what? You could think about that as being L sub j divided by L sub j,